Hey, welcome to this third video in a series of factoring videos. If you're here, you should have already watched the video that overviews factoring, as well as the one that teaches you how to factor using greatest common factor, also known as undistribution. We're going to continue on here and show you the next method in this series of methods of factorings, and it's using factoring techniques that allow you to factor a difference of two squares. So let's drill down here a little bit into difference of two squares and start to make a submap in the concept map. Okay? And let's see how this goes. The first thing I want to tell you is that when you factor a difference of two squares, it's the first factoring you're going to use that has a special pattern. There's literally just a pattern that you use to do the factoring. And let's talk a little bit about prerequisite skills here for doing the factoring, okay? And that is going to be one, is you have to be able to identify a perfect square. And two, you've got to be able to square root the perfect square. There's a step when we do the pattern where it's obvious you're going to need to take a square root, okay? And then three, you're going to need to be able to FOIL proficiently, because this will allow you to check your problem. Again, FOIL and factor are very much reversible ideas, so it's hard to talk about factor without talking about FOIL. I'm going to show you this as a stepwise method, so hopefully we'll put some steps up here for how to do these problems. And we'll go from there. So let's take a look at these prerequisite skills just for a moment. Identifying a perfect square and square rooting a perfect square. So to do that, we need to make sure that we can identify perfect squares. Now, identifying perfect squares should be decently easy when there's not a variable. You should have a sense of that already, and those are just 1, 4, 9, 16, 25, 36, continuing on. You really should know them up to 12 squared, which is 144. Okay, that magic list is very important. Okay, and it's just gotten by doing 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, etc. up to 12 squared. Okay? Now, when there's a variable involved, it's just a rule that you need to remember, and that rule is that the exponent must be even. Okay? Anytime you square something that has an exponent, you would double the exponent. This always creates an even exponent. So you have to see that the exponent is even. So let's just make our way through this list of examples and sort things out by being squares or not squares. Okay? So 64 is obvious. It's a perfect square because it fits in this magic list. So there's not a lot of thought to do there. It's 8 squared. X squared is good too because it has an even exponent, and you would think that something called x squared is a perfect square just by its sound. 8 to the 24th, even exponent, it's a perfect square. Now 50. 50 doesn't fit in this list nicely, okay? Its square root is a decimal, so it's not what we call a perfect square in terms of it having an integer square root. Now 81x, confuses kids sometimes because 81 fits in this list because it's 9 squared. But the exponent on the x is odd. Therefore, this is not a perfect square. Moving on to 16x to the 4th y squared. 16's in the magic list. X to the 4th is an even exponent, and so is y squared. This is, in fact, a perfect square. Now, z to the 9th. Some kids say, oh yeah, 9 is in this magic list. It's good. But if you also think about it, 9 is an odd exponent, making it bad. Okay, don't be thrown off when the exponent is a perfect square. That doesn't make the factor a perfect square. Okay, so taking square roots. Taking square roots is pretty easy in terms of the coefficient, okay? The multiplier of the variable. If it's a perfect square, you just square root it the way you normally would. And for the exponent rule to square root is cut the exponent in half. Okay, and this makes sense because when you square something that has a variable, you double the exponent. So when you go to square root it, the reverse of that would be to cut the exponent in half. Okay, so we see that if we're going to take some square roots here, everything in this list is a perfect square. So what is the square root of 25x squared? it's 5x. And 36x to the 10th is 6x to the 5th. Again, noting that I am cutting the exponent in half. And when I cut 2 in half to get 1, I don't write the 1. Continuing on, we see that it's going to be a to the first, not written with the 1, y to the 4th when I square root this next term. Now, 100x to the 16th, some kids get it wrong and say it's 100x to the 4th because they got to square root the 16. But again, the rule is to cut the exponent in half, so it's actually equal to 100x to the 8th. Okay? So there's some of our prerequisites in terms of identifying perfect squares and taking square roots. Okay? So let's take a look now at this special pattern for perfect squares. We see that this is a difference of two squares because it's a subtraction, and I have two terms that have even exponents, and those terms are obviously squares because they say squared. Well, we can factor that into the following product. It's two quantities, okay, of L plus R and L minus R. Okay, well, the relationship that you need to see here is related to square roots, because how do we get from L squared to L? Well, you just take the square root, because if you notice, you've cut the exponent in half. Similarly, how do we get from R squared to R? Well, you take the square root. Again, because you've taken the exponent from 2 and made it 1. Okay? So all you need to be able to do to emulate this model, this pattern, is to identify that you have a difference of two squares and take the square roots and write them in this order. Once is a sum, once is a difference, and then create the product by having these quantities here, which makes it a multiplication problem. Now, just to prove that these two things are equal, I'm going to take a second to FOIL this all out. You can take my word that they're equal, but let's just show it. Okay, so what do we have here? We've got L times L is L squared, and L times negative R is negative LR, and R times L is RL, also known as LR. It's positive, so I write plus, and then plus R times negative R is negative R squared. Well, we see we have like terms in the middle, and in fact they're inverses of each other, so they cancel, leaving us with L squared minus R squared. And obviously that is the same as the original. So we see that beyond a shadow of a doubt, these two expressions are equal. Okay? Well, let's look at some examples now. Okay? Factoring with differences of two squares, steps. So, step 0, I tend to write step 0 in some of my steps because it kind of implies that not every problem requires that you do it, but you should at least look for it on every problem. And again, it's factor with GCF if possible. We joked around earlier about how saying GCF could also stand for gotta come first, because we want to drill it into our brains that no matter how we're factoring, we always want to look for a GCF. Okay? Then, after we've moved past that step, in all these problems, we'll probably deal with differences of squares. So just confirm it's a difference of two squares by saying that it's, a number from that magic list of squares and all the exponents are even, and especially, though, that it's a difference, which means it's a subtraction problem. Okay? Once you do that, use a special pattern. Okay, so let's factor in these, and we'll fully factor, which means we'll factor our factors if possible. Okay? So is there any GCF in x squared and minus 100? And there's not. So then I note that we've got 100 is a perfect square, the exponent here is even, and I have, in fact, a subtraction, which makes it a difference. Also, you want to note that there's a 1 in front of the x squared, which is great because 1 is obviously a perfect square. So the only thing I need to do is set up my two quantities. That'll be the product. Once for plus, once for minus, and then I'll square root my x squared, which gives me x, and then I will square root my 100, which gives me 10 and 10. So the answer to factoring x squared minus 100 is the quantity x plus 10 times the quantity x minus 10. You could FOIL that out and check that and see that they're equivalent. In this next example, where it says 25b squared minus 81, I look for a common factor again, first, okay, and I see 25 and 81 do not have common factors, and the b only appears in one term. I do notice, however, it's a difference of two squares because it's subtract. 25 and 81 are in the magic list of squares, and the exponent is even. So I just apply the special pattern again by setting up two quantities that have a product, one with a plus, one with a minus. And then I'm going to factor 25b squared into its square roots, and I'll get 5b and 5b. And then I'm going to factor 81 into its square roots, and I'm going to get 9 and 9. If I FOILed that out, you could pause the video and do that if you'd like, you'd see that I would get 25b squared minus 81. Okay, moving on to these next two examples. They're a little harder, okay, because they're going to involve multiple factoring. Okay, so first I'm going to try to see if there's a GCF that I could factor out in this problem. And I see when I look at 16 and 36, there is, and that GCF is in fact 4. So I'm going to set this up where I do 4 times a quantity, and I'll divide by 4 to get the remaining factor. You should have seen that in a previous video. I'm going to get 4a squared minus 9b to the 16th. Now, if I further examine this factor that's inside the quantity, I notice that we've got 4 and 9 are in the magic list, 2 and 16 are even exponents, and it's a subtraction. So this is a difference of squares. So I have to factor this quantity again, which means I'm going to bring down the 4 because I need to continue on with that being part of the expression. And then I'm going to set up two quantities as a product, one with plus, one with minus. And then I'm going to take my square root of 4a squared, which is 2a. And then I'm going to take my square root of 9b to the 16th, which is to do 3b to the 8th, because I'm cutting the exponent in half. Some people would say 3b to the 4th, because I want to square root the 16 and get 4, but that's incorrect. You square root a variable expression by cutting the exponent in half. Okay? So if I distributed the 4 back out and FOILed out the rest of the problem, I would get the original. So moving on to this next problem, x to the 12th minus 1. I again look to factor with a GCF and realize I don't have one. So I just want to see now, maybe is it a difference of two squares? Well, it is subtract. 1 is in my magic list, and 12 is an even exponent. And again, there's a 1 in front of the x to the 12th, and that's in the magic list too of squares. So I can set this up as a product of two quantities with the special pattern again, one that's plus, one that's minus. Then I could square root the x to the 12th, which just requires that, again, I cut the exponent in half, giving me x to the 6th. And then I square root the 1, which is just going to give me 1. Now, many people would think that you're done this problem because you've now factored it. But let's examine this second factor here for a moment. If we see this, we do see that it's two terms, it's a subtraction, the exponent is even, and 1 is a perfect square. Well, that means we could factor it again. Okay, so I'm going to pull down this first factor because I'm not going to do anything with that. But this second factor can be split into two factors, two quantities that make a product, one with plus, one with minus. And then I'm going to do the square root of x to the 6th, which gives me x to the 3rd, 2 times. And then I'm going to do the square root of 1, which is in fact going to give me 1, 2 times. Now, this can be all multiplied back out to be equivalent to the original problem. Okay, now, this is a question I always get when I do this. People say, Mr. Vizza, I see that you factored the second factor into those two factors. But why didn't you factor the first factor again? It had the same things in it. Well, that's not actually true. And again, if we notice the title here where it says difference of two squares, it's very simple. That is a sum of two squares. And there is no special pattern for factoring a sum of two squares. It's not even possible. So this just means if you notice the second factor that we had was a difference of two squares again, so we factored it. Okay, so now I guess that's pretty much it for examples. I'll go back to the flow chart, the concept map, and to do that I'm going to quickly take a picture of my steps here. Okay. And, oh, I got the tool there. I didn't want that to happen, so let me just get a new one. Okay, so I'm going to take that, go back to my concept map, and I'm going to paste those steps in so that they become a important part of this process. Okay? And I'm going to try and finish this concept map up here to review again just a little bit. Okay? Again, those steps are to factor with GCF if possible, confirm that you're doing a difference of two squares by our knowledge of what it means to be a difference of two squares, and then use the special pattern. Okay? So what we have here is just to review that special pattern is in fact when given the difference of two squares, we factor it into the sum of the square roots times the difference of the square roots. Okay? And again, those prerequisite skills is where really most of the work is. One is identifying a perfect square. Well, if it's non-variable, you have to make sure you know that list of numbers. Okay? Again, 1, 4, 9, 16, 25, 16. Excuse me, I had to make an edit there just briefly. But again, that list is 1, 4, 9, 16, 25, 36, etc. It does go forever. We do want to also recall that the exponent just has to be even, otherwise you won't get a perfect square. And then what else do we need to know there with that? Is that for square rooting a perfect square, when we're dealing with the exponent, you need to cut it in half. So this video was a little bit long. It went in detail. You really shouldn't need a lot more information to be successful with the difference of two squares. So I would try some practice problems, rewatch it in parts that you need, take a good stare at this concept map and try and commit it to memory in some ways. That's a lot of good information here. So hopefully you will enjoy and move on to the next factoring video as well.